We're going to talk about trees and forests. Trees and forests go together as naturally as the terminology would have you expect. Tree models are setting a number of decisions to classify where each classification creates branches and a number of levels as the branches expand out. For instance, if we wanted to model whether kids need mental health treatment, we have info on kids' age, lots of other data. We want to see which are important. Each yes-no question branches out. It creates a model that looks something like a tree with all those branches. The X variables can be continuous or discrete. For instance, does the person have a college degree? That's discrete. But also, how old are they? Where the model can pick one or more breakpoints for the age. Each of these explanatory variables, the set of X, is called a feature. That's just the terminology that's used. The tree model splits based on the X variable features, trying to find splits that give the greatest reduction of the sum of squared errors in the Y. It's useful to understand that the goal it's seeking is very similar to the goal of ordinary least squares or other models such as logit or probit. There are many common parts of these estimation strategies because it works. There are other techniques that might minimize variance of the objective function, maybe minimize the absolute value of the errors instead of the squared errors, but minimizing squared errors is the most common. How do we do that in R? Common libraries are rpart or caret. I don't have a strong preference for one or the other, but I'll demonstrate with rpart. It creates partitions that look like trees, as you can kind of see in the picture. The model does explain whether a person has whether the kids need mental health coverage, and choose to use any of the variables in the model. The syntax is straightforward, very much what we're used to. We just use rpart in place of lm, add method equals class to tell it that our y variable is 0, 1, dichotomous to be classified. If the y variable were continuous, then we'd use ANOVA. And that CP is just tells it to sort of back off and allow a whole bunch of different branches. That's one tree. Estimating one tree, however, takes a certain artistry, since sometimes they can end up using too many features that explain within our training data but don't generalize very well. The tree can get too bushy, is the phrase, and it would need to be pruned. Yeah, sorry. Maybe folks took that metaphor too far, but that's genuinely what the terminology is. Anyway, the trees might get too many branches that meticulously classify the particular training data, but might not be very useful at making predictions out of sample. Statisticians try to figure out the optimal amount of pruning needed. Or we could estimate a whole bunch of slightly different trees on slightly different training sets, and that would give us a forest of tree models. Each tree grown on a random subset of the training data, and that gives us the forest. The forest model would aggregate the predictions of a set of trees. So for instance, if 70% of the trees predict some outcome, then that's the best prediction in the forest working in ensemble. Now you could create trees one by one, but that's pain. It's just better to set the computer to work. It takes a lot of computing power and time, but it's not difficult. But random forest models are very difficult to explain. While trees are simple, those are set of decision rules. It's one of their real value. But a forest is mostly a black box. It's a set of tree models that voted on an outcome based on some amount of randomness of data selection. It's tough if one human has to explain to another human why some decision was made. Now, if the point is just get a prediction, especially if that prediction is low stakes, then a forest can be very good. For instance, credit scores. Those determine if somebody gets a loan and what interest rate they pay. It's important, in fact legally obligated, to have a rationale available. So that's not a forest. Kathy O'Neill has a great book on this, Weapons of Math Destruction. No, I'm not lisping, that's math destruction. It's a problem for lots of public policy if decisions are made that have no available rationale or justification. Perhaps they use data sources that deepen existing inequalities based on gender, race, or ethnicity. It can be a really big problem if you're making high-stakes decisions. But how to implement random forest in R? There's a package. First, though, we use the standardized package. That puts the variable, all the data into a standardized object, which squishes all the variables into the 0-1 interval, which recall we did back with K and N, and puts them together consistently and coherently so we can run lots of different machine learning techniques. Each one starts with the exact same data, and it's easier to compare. The next step is to call the random forest using that first line of code, print the output and variable importance. There are two different measures of importance. Don't worry about too much for now. We get the predicted values to the model, compare them against the actual value for the test set. That is the new data that's not within the training data. That's the model hasn't seen yet. That can help test if the model is useful. This is called the confusion matrix. Yeah, it's a lot of my life, but this is good terminology. I mean, machine learning is kind of cool stuff, but I wonder how much it comes from the good terminology. If they called it the matrix of type 1 and type 2 errors, it wouldn't be so cool. The consolations of philosophy. Anyway, the confusion matrix is a 2x2 table that compares the predicted values against the actual values. The off-diagonal terms are the errors, and those should be small. But remember, as we've said previously, that false positives or false negatives might have a different cost. So there's no guarantee the cost is symmetric. You should be asking, which mistake is less costly? And that depends on the point of the model. Often you'd also look at particular subgroups to check if there are some groups where observations are more confused than other groups. That can help refine the model accuracy.